In this example, we will find the first four non-zero terms in a power series expansion about x equals 0 for the solution to the initial value problem 2 times y double prime plus x times y prime plus y equals 0 with initial conditions y at 0 equals 4 and y prime at 0 equals 6. So we're doing the power series expansion about x equals 0, so all of the terms in our power series expansion are going to be of the form y equals sum from n equals 0 to the power infinity of a sub n x to the power n. And if we write that out, we get a naught plus a1 times x plus a2 times x squared plus a3 times x cubed plus etc. And the problem asks for the first four non-zero terms, and if a0, a1, a2, and a3 are all non-zero, this is what it's asking for. So unless one of the coefficients is 0, it's basically asking us to find what is a0, what is a1, what is a2, and what is a3. So again, this is assuming that all these values are non-zeros. So we may have to go to a sub 4 or a sub 5. Now, another thing to note is that when you have the power series expansion here, we can see that y at 0 is a0, right? Because if we plug in 0 for x, all these terms disappear. But that, together with the initial condition, tells us that a0 equals 4. So we already have one of our four non-zero coefficients. Now y prime, we have to do the termwise derivative, so that's n times a sub n x to the power n minus 1, and then n equals 1 to infinity, and it gives us a1x plus a2 times, or 2a2x, sorry, this gives us a1, right? Derivative of a0 is 0. Derivative of a1 times x is a1. And then plus 2 times a2x plus 3 times a3x squared plus etc. But what we see now is that y prime of 0 equals a1. Because again, if we plug in 0, all the higher order, all the higher coefficients, a2, a3, a4, will cancel out because of the 0 for the x, and we're left with a1. So that tells us that a1 is equal to 6. And now we have two coefficients already. Now the other two coefficients will be a little bit more work because what we have to do is we have to plug this into our differential equation. So we also need y double prime, and the summation starts at 2 and goes to infinity, and we take the derivative of this right here, so that's n times n minus 1 times a sub n x to the power n minus 2. And if you write that out, it gives you 2 times a2 plus 6 times a3x plus etc. So plug that into our original differential equation. So our differential equation is 2y double prime plus x times y prime plus y equals 0. So that becomes 2 times, and then y double prime, sum from n equals 2 to infinity of n times n minus 1, a sub n x to the power n minus 2, and then plus x times y prime, and that's the summation from n equals 1 to infinity of n times a sub n times x to the power n minus 1, and then finally just plus y, and y is the sum from n equals 0 to infinity of a sub n x to the power n. And all of that equals 0. So now what we want to do is we want to simplify this, and then we want to combine those power series. So the first power series is sum from n equals 2 to infinity of 2 times n minus 1 times a sub n x to the power n minus 2, and then plus summation n equals 1 to infinity of n times a sub n, and this turns into x to the power n, because the x to the power 1 times x to the power n minus 1 gives us an x to the power n, and then summation n equals 0 to infinity of a sub n times x to the power n, and that equals 0. So the nice thing about combining these three series is that the latter two already have x to the power n. And so what we can do is we can introduce a new counter here and basically say I'm going to replace the n by k. And then for the first one, I want to replace the n minus 2 by k. So another way of writing this is that n equals k plus 2. So we're now going to replace the n by k plus 2, and then the n minus 2 becomes a k. So that first sum now changes into k plus 2 equals 2. To infinity, and then 2 times k plus 2 times k plus 2 minus 1, and then it's a sub k plus 2, and then we have x to the power k. And then I can already combine the other two into one sum. Well, actually, I cannot just yet because they don't start at the same n value. So I'm going to keep that for now. And I'm just going to replace the n by a k. So I can just write the sum from k equals 1 to infinity of k times a sub k x to the power k plus summation k equals 0 to infinity of a sub k x to the power k, and that equals 0. So let's clear this up a little bit. So that first sum is actually from k equals 0 to infinity, and then 2 times k plus 2 times k plus 1 times a sub k plus 2 times x to the power k plus summation k equals 1 to infinity k times a sub k x to the power k plus summation k equals 0 to infinity of a sub k x to the power k equals 0. Now, in order to combine these series, they all need to start at the same value. So I would like for all of them to start at 1. So what I need to do is I need to take a look and see what happens for k equals 0. So for k equals 0, if I plug that in here, what I get is 2 times 0 plus 2 times 0 plus 1 times a to a sub 0 plus 2, and then x to the power 0, that will just give me times 1. So if I plug in 0 here, that happens in the first term. And then for the second part, there is no k is 0, so that doesn't contribute anything. And then plus what happens when k is 0 here, I get a0 or a naught, right? Because again, x to the power 0 will be 1. And that should still be equal to 0. Because if I let x be equal to 0, all the other terms disappear. So this needs to be equal to 0. And if I simplify that, I get 2 times 2 times 1. So that's 4 times a2 plus a naught equals 0. But I already know that a naught is 4. So it follows that 4a2 plus 4 equals 0. And so a2 is equal to -1. So that follows from the fact that a naught equals 4. Okay, so if we ignore that first term for these two series, because that will add up to 0, we can now combine all the series. So we're looking at the sum from k equals 1 to infinity of 2 times k plus 1 times k plus, so k plus 2 times k plus 1 times a sub k plus 2 times x to the power k plus the summation from k equals 1 to infinity of k times a sub k times x to the power k plus summation k equals 1 to infinity of a sub k x to the power k, and that equals 0. So again, I can ignore the k equals 0 because I looked at that case separately and I found that a2 is equal to -1. And so now we're looking at the case that k is greater than or equal to 1. So now if you look at the coefficients, so this is the coefficient in front of x to the power k here. This is the coefficient over here, and this is the coefficient over here. So in order to have this expression be equal to 0, these coefficients, when you add them up, they have to equal 0. So what we get is that 2 times k plus 2 times k plus 1 plus k times a sub k plus a sub k, that equals 0 for k greater than or equal to 1. And that will turn into a recursive relation. So and I notice here that I forgot to include a sub k plus 2. So let's solve this for a sub k plus 2. So I can write this as 2 times k plus 2 times k plus 1 times a sub k plus 2, and then that is equal to minus, so this is 1 plus k, so this is minus 1 plus k times a sub k. And then I can divide both sides by 2 times k plus 2 times k plus 1, and I get a sub k plus 2 equals negative k plus 1 over 2 times k plus 2 times k plus 1. And what we see is that a k plus 1 actually factors out. And so our most simplified recursive relation is a sub k plus 2 is equal to negative 1 over 2 times k plus 2 times a sub k. That is our recursive relation for the coefficients. Now, at this point, we're almost there. We already have 3 non-zero coefficients. So if A3 is non-zero, we're done. So recall that this recursive relation holds for k is greater than or equal to 1. So let's plug in a k equals 1. And what we get is that a sub 1 plus 3 is equal to negative 1 over 2 times 1 plus 2 a sub 1. Or a sub 3 is equal to negative 1/6 times A1. So now we need to look up what we had for A1. A1 is equal to 6. So this is equal to negative 1/6 times 6. And so that equals negative 1. And now we can figure out what y of x is. Y of x is a naught plus a1 times x plus a2 times x squared plus a3 times x cubed. And we found that a naught was 4. We found that a1 was 6. We found that a2 was negative 1. So that's minus x squared. We found that a3 is negative 1. So that's minus x cubed. And so those are the first 4 non-zero terms of the power series expansion of y.